So what I have set up now for the simple switcher to test the output load variation and how it responds to different frequencies and also step loads and things is I brought in my, it's a Darlington N-channel transistor with a 1 ohm load in it, and I've put that directly across the output of the switcher, and what I'm doing is I'm driving the base through a 1 kilo ohm resistor to my Adjuvant 33622A frequency generator. And what I'm doing right now is I've just got it in DC mode so that I can gradually increase the drive to the base of the transistor. And what I'm doing is I'm monitoring the volts across the 1 ohm resistor. It's only a 5% resistor, but it's close enough for this experiment because it's not about being precise, it's about being stable and just being able to track roughly what we're doing. So on the right hand meter we're measuring the millivolts across the load. So if it says 1 volt, then basically that's going to be 1 amp. So 2 volts will be 2 amps, etc. Now theoretically this is capable of driving up to 2 amps on the output. I don't know whether that is limited on 3.3 volts, so maybe there's some power limitations in there, or whether it's literally allowing the 2 amps even at the 5 volt range, but we're leaving it at 5 volts for the moment. And as you can see, I've got the output of the power supply turned on. It's currently set to deliver 10 volts, nothing more. And you'll see on this meter here that the volts is currently reading 5.126 volts on there. Let me just adjust that. There you go. See that a bit better. So that's because there's no load currently on the output of the simple switcher. So obviously it's crept up by about 50 millivolts, which with no load that's quite reasonable. The caps will charge up and there's nothing to pull them down and things like that. Obviously the current is reading 200 microvolts right now. We're on the millivolt range. I'm not going to leave it on the millivolts because we're going to rapidly exceed that. So it's reading about 200 odd microvolts. And that's basically, it's turned off, but there might be a little bit of leakage current. There's certainly nothing being detected on the power supply. And the output of my, I guess it's got a few millivolts on the base of the transistor. So let's just set that to 0 there. Alright, so I've got 0 volts on the base. So let's start cranking this up. Now I don't expect to see anything until we get to about 700 millivolts or so on the base of the transistor, but let's just start cranking this up until we start to see a current flow. So we're about 400, 500 millivolts, 600, and we're just starting to see the least significant digit of the current sensor changing here. 3, 4, probably going to see 800 millivolts on the base right now. See where it starts to 1.6 volts there. We're starting to creep up now. Yeah, having a direct effect on it now. So we've got 2 volts. So let's take it up till we've got 100 millivolts on here, which would represent 100 milliamps. That's 3 volts. Alright, so a little bit less than just adjust the voltage a little finer here. All right, close enough. So we have 59 milliamps being drawn out of the power supply, and we've got 100 milliamps going into our load at 5.04 volts. So what I'm going to do is I'm going to increase the drive, and what we'll see is this current go up, unless we're just going to watch to see what happens with the output voltage for the moment. What we'll do a little bit later is we'll set up a square wave going into the base of the transistor to literally switch it from maybe 100 millivolts, 100 milliamps up to the full 2 amps, and see what effect that has on the output on the oscilloscope. But for now, let's just do the static test and see where we go. So this is at just under 3 volts. We've got 100 milliamps. So now I'm going to start cranking it up. So we're going to take it up to about 500 milliamps. Okay, so we're still reading 505. Let me just stick that back down again. Still reading 505. I'm back down to about 100 milliamps again. So that's staying. The output voltage is not drifting at all with the changes in current at the moment. That's a full amp now being drawn out of the switcher, and it's staying rock steady at 5054. Let's go up to 1.5 amps. So it's just dropped on the least significant digit here, 5053 now at 1.5 amps. So let's just keep going up and see where 5053 still. It's dropping a little bit more. Part of this, where is it? No, I've got the measurement directly on the terminals of the switcher down here. If we just have a quick zoom in there, you'll see. You can see that I'm measuring directly on the output terminal, so the lead resistance to the load and things like that is having no effect. The load isn't getting particularly warm because it's only a watt or so, and it's a reasonable size heatsink on it. I'll just show you that. All right, we've got the Darlington power transistor. It's capable of handling about 15 amps and 300 odd volts. It's quite a powerful one that I'm going to be using for DC load or something later on. And I've got this 1 ohm resistor as well sitting in series with it. And it's warm, but it's no warmer than, you know, maybe 25 degrees or something. So the output current right now on the switcher, if I go back to the meters, you'll see is sitting at 1.7 amps. I'm going to leave a close up of the meter there because looking at the switcher really does nothing, because there's nothing to see happening here unless something starts smoking, in which case I'll move the camera to it. But for now, we'll just have a look at the meters here. So that's got 5.24 volts on the base of the transistor. So let's just drive this up to 2 amps now, which is the theoretical maximum for the switcher. So that's 2 amps, and we're reading 5051. So if I just go back down to where we were before, which was, I think, 2.94 volts on the base. There's my enter key. Volts, there we go. So that's taking it back down to the 100 milliamps. There's a low pass filter on this right hand meter. Let me just try and take that off. Okay, should respond a little quicker now. Yeah, let me just take that down one more count. So, yeah. I think the transistor's warmed up a little bit now with passing that current through, so it's responding to slightly different voltages now. So that's 100 milliamps, and we'll go back up to 4.5 volts on it. I can't remember exactly which one I had now. So that's taking it up to 1.2 amps, and basically it didn't have any difference there whatsoever really to speak of on the output. Last digit, so 1 millivolt is really all was changing. So now let's crank this up a bit further. We're drawing 1.19 amps out of the power supply. This is providing 10 volts into the switcher at the moment at 1.19 amps, and we're outputting 5 volts at just over 2 amps. So we've got about a 10 watt load on the input, and we have about a 12 watt draw on the power supply. So we've got 10 volts at 1.19, so 1.2 amps, which is 12 watts. So we're sitting there up in the order of, you know, sort of 85-90% efficient, which is not too bad. Usually these devices don't work to their best at the top end of their range. They're usually somewhere in the middle where they're most efficient. So we'll see if we can figure that out once we do a few spot checks and we just put it into an Excel spreadsheet or something and see what it reads. Anyway, I'm going to take this up a little bit further and see how far it'll let me go. 2.2 amps. Let's go up a little further. 2.3. The output's still 505, so that's still holding good. I'm not sure what's going to give up first, my power supply, because it's now outputting 1.4 amps. And I got 2.43 amps here. It can only go up to 1.5 amps on the power. Oh, there we go. It's just started to drop off now on the switcher. That's 5. As soon as I go above 2.5 or 2.4, 2.48, it's now dropping off, and there it's gone. It's dropped down to 1.5 volts now, and the current's dropped right off. So if I back that off just a little bit, I'll probably get it back again. There. So about 2.3 amps. So it's rated at 2 amps. We're actually able to pull out about 2.3, almost 2.4 amps out of this thing before it keels over. So that's actually pretty good. Now let's see what happens when let's hook it up to an oscilloscope, and I'll set the frequency generator to put a, I don't know, something like a 10 hertz square wave switching between about 6 volts. Let's see where it's at 2 amps. Let's be fair with it. So about 5.5 volts at the top end, and I think 2.4 volts on the low end. No, a bit higher than that, I think. So 2.8 volts on the low and 5.5 on the high. I'm going to set up a square wave on the frequency generator to do that, so I'll be right back. Alright, so what I've got now running is, if I just go through the various devices that are involved in this little test, just zooming into my frequency generator here, you'll see that right now I've got 200 millihertz, which is basically every 5 seconds it's going to change state. And it's going at an amplitude of 2.4 volts peak to peak, and I put an offset of 4 volts. So basically it's switching between just over the switch on voltage of the transistor up to pretty much the full 2 amp range, which would be basically 2 volts on the resistor when it's running at the 2 amps. So I'm not worried about it being exact, because really what we're looking for is how well the voltage responds to the large changes in load here. What I will do is I'll increase the frequency a little bit later, but for now that's what I've got coming out of my Agilent waveform generator. And let's go now to the meters. Alright, so what you're going to see here is the left one again is the voltage across the load when it stays on at 5.05354, so that's staying pretty consistent. The right hand side one again is reading the volts. Let me just put it back to fast mode again. So it's reading from 1.8, 1.9 volts, and then it's going down to about 100, just over 100 millivolts. So it's up now, 1.7, 1.8 volts. So it's 1.8 amps down to about 100 milliamps. So that's a pretty good dynamic range check, I think. Right, as I say, right now we're just running it at 200 millihertz. So every few seconds it's switching. Now let's go up to the oscilloscope and see what's happening here. All right, so I've got it on a slow scale right now, because I want you just to see the blue trace is the current, and you can see there's a little bit of a curve on it, and that's probably because the waveform generator is outputting a very nice square wave, but the transistor is probably warming up a little bit when it first gets turned on to the high current and cooling off when it's coming down just a bit. And that's probably affecting the current flow, and as well as the resistor is probably going to be getting a little bit warm as well. But you can see here the yellow trace, I've set it to be 1 volt per division, and certainly right here I can't detect any deviation in it whatsoever at that frequency. So what I'm going to do is I'm going to increase the frequency to 1 hertz basically on the switching, so that we can increase the oscilloscope. So let's just do that now. That's done. Now my meter down here for the current is basically useless, because it's not going to be able to keep up with the switching of the current. But you can see here that the volts right now seems to be pretty stable. So let's just pick the current input for the trigger, and we'll have to reduce the volts now because the current one is running at 500 millivolts. So let's bring down the trigger. So now we're triggering run again. So we're running there nicely now, triggering on that waveform. So I'm going to increase the range of these signals so that I can get them. But what I want is I've just moved the current switching down a bit so that we can compare it. And what I'm going to do now is I'm going to change the voltage range of the input. My multimeter function is messing around with my, I've got auto range on it. So let me just take the multimeter off on the screen for a moment. Okay, so we've got the channel 2 now monitoring. Let me just switch it to 500 millivolts. We've got channel 2 monitoring the current across the load, and we have channel 1. Just move that up a little bit so channel 1 is monitoring the voltage. I'm just going to turn off some adjacent lights here. Perhaps you'll be able to see the display a little better. That's good. So what you can see here, if I just single shot this for a moment, is every time the current increases to the maximum here, which is about 2 amps. Remember, this is on 500 millivolts, so it's not going quite to 0. So it's if I adjust that so that it's actually sitting on 0 there, so it's 500, 1 amp, 1.5 amps. So it's just under 2 amps switching is what we're doing there, and it's only increasing the noise by a few millivolts on that. I'm going to increase the settings on the channel 1 and see if we can get a bit more sensitivity on that. So the nice thing is that offset that I found for this oscilloscope, for the Tektronix MD-03054, it's actually remembering the offset and sticking to it. So now that I'm increasing the sensitivity, so we're down to 100 millivolts here, it's actually doing quite a good job of staying centered. So that's a really nice feature there that I'm going to be relying on quite a lot in the future. So this has now made it a little more obvious. Every time the load is increasing, you can see a massive increase in the switching frequency probably showing through now of the switch mode controller. Excuse me, sorry about that. The switching frequency is definitely bleeding through here. I think if we increase the time base, let's just do a single shot here and capture that, and we'll see if we can increase it and see what that is. And it's probably going to be the switching frequency of the power supply. So that's the output response to the switching current. So we're sitting at 5.066 volts. You can see it dropping there and then recovering back up after about 150 microseconds. It's dropping by about 150, nearly 200 millivolts. And then it recovers very, very quickly. I don't think anything would normally be able to do much better than that, and this does have room for an extra larger capacitor on the output if you wanted to improve on that. So the next signal, actually I'm going to try and capture some of these to memory so that we can have a look at them later. Figure out how to do that.